Alright, welcome. So now that we're in our energy unit, we're going to be seeing a lot of physics problems that have to do with two things: kinetic energy, the energy of motion, and potential energy, the energy contained in objects that have yet to move or do something productive. So this particular problem is about potential energy. We're going to see that it's about a parkourist, someone who does parkour and runs along the rooftops of buildings, something that we can all relate to. So in this particular problem, here's the issue. A 70-kilogram free runner, otherwise known as a parkourist, stands on the roof of a 150-meter building. There's a second building, so there are two buildings in this problem. There's the 150-meter building, and then there's a second building that is next to the one he is currently standing on, and that one is 90 meters tall. So there's a 150-meter building, and there's a second 90-meter building. How much potential energy does the man have relative to, this is going to be extremely important to the problem, not for the first step, for the steps that come after part A. How much energy does the man have relative to the ground, the adjacent building, and the roof that he is currently standing on? First thing we always want to do in these physics problems, just to make things easier on us, if it's a kind of difficult problem to interpret, if you're not really sure what's going on, draw a picture. Draw a diagram of the situation. That'll make it easier to imagine what's going on here. So I'm going to go ahead and put a picture up here. Boom, and there's a picture. So here's the guy right on top, our free runner. He's standing on top of the 150-meter building. The problem says there's a building right next to him that is 90 meters tall. That's right here. And then, of course, he's near the ground because, as we all know, if you walk off the building, the thing you're going to meet is the ground. So they're the three things we're dealing with. Now, here's the first problem. How much potential energy does the man have relative to the ground? So for that, all we need to know is our equation for potential energy, because just like with anything in physics, we can figure out how much energy or how much anything something has by just doing a simple calculation. For that, that's going to be the potential energy equation. So if you recall what that is, it's just potential energy equals the mass of the object that we're talking about, which in this case is the mass of the free runner, multiplied by the acceleration due to gravity wherever the object is. So this guy is relatively close to the Earth's surface, so we're going to just say that's 9.8 in this problem. And then multiply all of those two things by height, the height of the object that we're analyzing here. So those three things are going to come into play. We're just going to multiply those three factors together, and we'll have how much potential energy is inside that free runner. So relative to the ground, the reason that we're specifying relativity to different locations here is because potential energy is always a kind of reference between 2 points, because we talk about height. So if we're looking at the height of this man right now, his height compared to the ground is going to be 150 meters, because he's standing at 150 above the ground, and we're saying relative to the ground, how high up is he? So 150 meters. That's easy. So we're just going to do our calculation now of potential energy, and we'll find out how much energy does he have relative to the ground. So I'm going to zoom in here, a little more space to do my calculation. All right, our potential energy we know is going to be equal to mass times gravity times height. Can't see those numbers on the screen right now, but I'm just going to recall them. The mass of this free runner was 70 kilograms, so I'm going to plug in 70 here. That's going to be multiplied by the acceleration due to gravity, which is a factor we've used all year. That's going to be 9.8 for any object that's near the Earth's surface. And then we are multiplying those two things by the height of the man, which we are just saying is 150 meters. That's how tall the building is that he's currently on, and we're referencing to the ground, how high up is he? 150. Now, if you were to calculate all of those together, you would find that that calculation gives you 102,900 joules of energy. Again, just a reminder, we're seeing how much potential energy does this man have when he's on top of the building. Whenever we measure energy, whether it's kinetic energy, potential energy, solar energy, any type of energy we could possibly talk about, joules is going to be our standard unit. So here would be our final answer for part A. We have 102,900 joules. And if you wanted to make this a little bit of a smaller number, you could even call that 102.9 kilojoules. But, not necessary for this problem. So that was for the ground. Here's where the problem gets a little more complicated. We start having to actually really know what they're talking about when they ask us about potential energy. So in part B, they ask, how much potential energy does this man have relative to the adjacent building? So we're not talking about the ground here anymore. We're talking about this height right here, the height of the top of the building. If he were to jump from this building that he's currently on to this one, how far would he fall? That's going to be 150 meters minus 90 meters, because this is the height he starts out with, this is his final height. So the difference between those two is going to be 60 meters. So the reason we're going to solve this problem using the difference in height between the two buildings is because potential energy is essentially just saying, here we go, potential energy is essentially just saying, what is our potential to do work? What's our potential to actually fall and move due to gravity? So some things here are going to stay the same as in the last problem. His mass hasn't changed, gravity hasn't changed, his height, that third factor there, is the only thing that's changed. So this right here, you can't really see it off the screen here, but height is going to change, gravity will stay the same, mass will stay the same. So I'm going to put down his information here. His mass is still 70 kilograms. Acceleration due to gravity, he's still relatively close to the surface of the Earth, so we can safely say that 9.8 is the factor of gravity that's going to be affecting him. And his height now has changed. Even though location-wise, the free runner hasn't moved from where he was before, so he's still technically at the same height, but this is a different type of question than just asking how high up is he on his own building. It's asking what's his height compared to another location. So his height on this building compared to the ground, yeah, is 150 meters, but his height on this building compared to this building is much less than that. Another way you can think about it is, if he jumped to this building, how much injuries might he sustain? And if he jumped off of this building, how many injuries might he sustain? Probably going to be in worse shape if he jumps down here. So it's going to be safer down here because he has less height compared to the building that he's currently on. Less distance to travel here. So he's going to be safer going here. That's because he's going to have less potential energy, which can actually turn into kinetic and have motion of energy as he falls. So what we're going to look at now is no longer his height from this building to the ground, but his height to this building here. That's going to be 60 meters, which you would know if you just did 150 minus 90. You'd get 60. So what I'm going to do is I'm going to go ahead and write 60 meters for his height. And that calculation just came from the 150 minus the 90. And if you were to calculate that out, you would find that you get an answer of 41,160. That's a 6 right there. 41160 joules. There's joules right there, having a little trouble writing. Joules of energy. Again, this is potential energy. Any type of energy has joules as our unit. So you can see, looking at these two numbers here, here's a huge number, here's a still a huge number, but considerably smaller, less than half. And that was because he just traveled down to a smaller height. And the reason that we have less than half of the energy that we had before was because he's traveling less than half of the distance he was before. If he went down to, say, 75 meters, which would be half the height of the building that he was on currently, right here, if we traveled half that distance down, we would have half the amount of potential energy. So we would have whatever this number is divided by 2. But in fact, he doesn't travel down to half his height, he travels even less than that. So that's why he has less than half the amount of potential energy he had before. So that would be our final answer for part B. And again, if you wanted to write this in a shorter way, slightly shorter in this case, you could write 41.16 kilojoules. But like I said before, not necessary for a full solution. So now finally we come to part C. Part C is asking, how much potential energy does the man have relative to the roof he is currently standing on? Now this is a tricky problem. This is mostly conceptual. You are going to have to do kind of a calculation, but not really necessary. First things first, let's just write down our equation, like we always do. Potential energy of an object in any situation is equal to mass times gravity times height. Has his mass changed? No. 70 kilograms is still the mass of our free runner. Has gravity changed? No. He hasn't gone any great distance away from the center of the Earth. or gone any closer to it. So 9.8 is still sufficient for acceleration due to gravity at his location. And then we have to multiply by his distance, or his height, compared between 2 points. In this particular case, he's currently standing at a height of 150 meters, and the place that we're kind of making that relative to is the roof he's currently standing on, which is 150 meters. So basically what this question is saying is, how high off of this building is he? And the answer to that is just 0. He's no height from the building. He's literally right on top of it. 0 meters of distance from the roof of this building. So we're going to consider for this part C that his height is 0. So I'm going to write in 0 here. And you can see where this is headed. I don't really need to even use a calculator here, because I know that anytime you multiply 0 through all of this equation right here, everything's being multiplied together, that zeros means that we're going to actually end up with a total of 0 joules of energy, OJ. 0 joules. He has no potential energy right now. Again, standing right here, in reference to the roof he's currently standing on, he has no potential energy because he is at the lowest possible point he can possibly be at. He cannot fall any further down to that building. He can fall in reference to the ground, and he can fall in reference to this building, but if he just stays right there in the middle, he's not going to fall anywhere. Gravity can do no more work on him. He has no more potential to do work because of gravity. Therefore, no potential energy. So how much energy does he have relative to the ground? Quite a bit. Relative to a tall building that's not quite as tall as the one he's standing on, a little bit less energy. How much energy does he have compared to where he's literally standing? None. So hopefully that illuminates these types of problems for you. You may see these types of questions on a test, and it's more important that you're able to analyze these conceptually rather than just whip out the equation and calculate the numbers that you see in the problem. Feel free to rewind this video and check out any parts that didn't quite make sense to you the first time around, and I'll see you in the next one.